Woohoo! We are live. This is Math 60 Intermediate Algebra. We're in section 2.2, and this is graphical linear equations in two variables. Woohoo! Which, if you are in Algebra 2, I'm going to assume that you have done this before. So again, this is not going to be the first step of introduction. This will be more of a review, as like if you're at a party and you're like, hey Bob, you know Sam, hey Sam, you know Bob, and then you can kind of walk away and let them talk to each other. So let's get started. An ordered pair is a solution of an equation if substituting it into the equation makes the equation true. So in other words, is this an X and a Y combination that satisfies the equation? So let me put that wording in. It satisfies, ooh, I got excited, the equation. Sorry about that. It satisfies the equation. Okay, so is the ordered pair 2, -3 a solution of the equation 3y equals 4.5x? It's an interesting question. So again, I'll remind you that ordered pairs, it's assumed that you've got an x and a y unless you're otherwise told. So in this case, x equals 2 and y equals -3. And if they're written as an ordered pair, then we want these things to be true at the same time. So these two are true together. So does this pairing make sense? So let's do what we call checking. So let's check. Woo. I've got 3y equals 4.5x. So in place of the y, I'm going to put in my -3 multiplied. Okay. I'm going to put a question mark there because we're not sure. And in place of the x, where's my blue? I'm going to put in my 2. So here's the x, which I've made blue, and here's the y, which I made pink. And so I plug in the y over here and the x over here. And let's see, on the left, I get 3 times -3, which is -9. And over on the right, I've got 4.5 times 2, which is 9. -9 does not equal -9. Nope. Not a solution. Now, it came really close. So I'm betting that you could look at this and go, wait a minute. If I just made that a +3, then this would be 3 times 3. That would be +9. That would have worked. So the problem was this negative. Or if you want the negative over on the left, what would the x have had to be? You're right. It had to be -2. So we can futz with this. This is a close enough. We got close enough that we could make some educated guesses about other things we could try. But that's not what the question asked. Question asked, is this a solution? Nope, not a solution. And of course, you could just write no. I was feeling silly to write no. Okay, is 4, 6, is that ordered pair a solution to the equation? Again, x equals, you're right, 4, and y equals 6. So let's check. Let's see. So I've got 3y equals 4.5x. So 3 times 6. Does that equal 4.5 times 4? So over here on the left, 3 times 6 is 18. Over here on the right, 4 times 4.5. 2 times 4.5 is 9. 4 times 4.5 is 2 times 9 is 18. You could do this on a calculator. Oh my gosh, look at that. It works. It satisfies this. Let me write this out. This ordered pair satisfies the equation. That's how you say it. So it is a solution. Woohoo! Part C, how many solutions are there to this equation? Any guesses? This is where math gets a little weird. Math is actually at its core kind of weird and really interesting. It turns out that if I just want two numbers so that 3 times one of the numbers equals 4.5 times the other number, there are an infinite number of solutions. Now, does that mean that every ordered pair is a solution? No, it just means there are a bunch of solutions to this. 4, 6 works. I would, spoilers, 40, 60 would work. 400, 600 would work. 4,000, 6,000 would work. Just for this particular setup, they're not always that easy. So there are a whole bunch of solutions. And one of the things that we're going to be working on in this section is trying to graph what those solutions look like, because I don't have time to write out all the answers, right? All the answers would take my lifetime plus everybody else's lifetime plus everybody else's lifetime into forever, to infinity and beyond. Woohoo. Okay, so let's move on to graphing. Woohoo. Graphing an equation, not just finding a single solution like we did, means to plot the entire solution set. This is the really bonkers thing. The entire solution set. So let's sit here. You are in Algebra 2 now. Algebra 1 was, just an introduction, and we didn't really stress some of the weirder parts of math because we don't want to freak everyone out. So, but now you've been sitting with math for a while. You've learned, you've got a lot of algebra. And I'm going to point out that this is kind of a bonkers question. I'm asking you to draw a picture of the entire solution set when I just told you that this is an infinite number of solutions. So an infinite number of points, and I'm like, yes, draw them right now in your lifetime, which normally you would say, nuh-uh. However, there's some really cool things going on. There's a pattern, and we're going to be able to take advantage of this pattern. So if an ordered pair is a solution of that equation, then it appears in the graph. So every point has to be accounted for. And there's another half to this. If there's a point that's on the graph, it has to be a solution. So it goes in both ways. Okay, so graph the equation y equals 3x minus 2. Hopefully you've seen a graph like this. You've seen an equation like this by setting up a table of values. So basically a table of values looks like this. It can be as long or short as you need it to be, and plot each ordered pair. So for this particular problem, I'm going to do a bunch of points. Now, in general, you might remember from algebra before, if you already know what kind of a graph this is going to be, you don't have to do a bunch of them. But since this is our first one in this class, I'm going to do a bunch of points. So what does it mean? Well, what I can do is I can start with a value for x, and I'm going to start with 0. I always try to start with 0. So when x equals 0, y is 3 times 0, I should have moved this over a little bit, minus 2, which is 0 minus 2, which is minus 2. So I've got the point, I'll write it over here, 0, negative 2, like that. That's my first point. Okay, I'm going to do 1 next. 1. 3 times 1, I just plug it in, I substitute it in. 3 times 1 minus 2 is 3 minus 2, which is 1. So I've got the point 1, 1. Okay, 2. 3 times 2 minus 2 is equal to 3 times 2 is 6. Minus 2 is 4. So it's 2 comma 4. Now, you might start to notice, I'm going up by 1 each time. You might start to notice that from negative 2 to 1, that's 3. And from 1 to 4, that is also 3. So you can start guessing what the next number would be. So if we went up by another 3, we'd expect to see a 7. Let's see if it follows that pattern. Math is all about patterns. Okay, plug in 3. 3 times 3 is 9, minus 2 is 7. Whoa. So this is a cool pattern to see. As the x's increase by 1, the y's increase by 3. That's interesting. I wonder if we will learn about that in the next section. Wow, let's I'm very excited. Let's stick around and find out. Now, generally speaking, I'm picking very specific points. You should be really nervous. And if we were in class, I'd be like, okay, you guys pick some points. Because if somebody's showing you only the points they want to show you, they might be trying to hide something. I'm not actually trying to hide something. It's just that we don't have an infinite amount of time. But what I will do is I can try some negative numbers. So 3 times negative 1 minus 2. Let's see. Negative 3 minus 2 is negative 5. Not my favorite, but okay. And in fact, we could even, I'm going to plug in the value 1/3 because you're allowed to use fractions. You can plug in anything you want in your table of values. A table of values is a collection of data to help you find the pattern. Now, in the wide world of equations in math, the graphs are not always going to be obvious. There are going to be times when maybe you have to do 20 points before you know even what's going on. So this is not the longest table of values ever, but it'll give us a good idea. So let's see, 3 times 1/3. You see how I chose the 1/3? Because 3 times 1/3 is what? It's 1. So it's 1 minus 2, that's negative 1. So I got 1/3, negative 1. Okay, so I've got 1, 2, 3, 4, 5, 6 points to plot on my graph. So I'm going to be thoughtful about this. And in fact, I may have been too excited. So let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh my gosh, I got very lucky. Notice that the biggest number I have to account for is 7 in the y's, and negative 5 is the smallest, also a y value. So I've got to be able to get it to go all the way down to negative 5 and all the way up to negative 7. Now in my x's are mostly positive, but I've got lots of room, so I'm not going to worry about that. So I'm just going to go ahead, where's my purple? And I'm going to draw my y-axis right kind of in the middle. And remember, I'm that one who gets very freakishly attached to the arrows. Okay, but now I want to be thoughtful about this, because if I put my x-axis right in the middle and I try to count up to 7, 1, 2, 3, 4, 5, 6, I'm not going to make it. So let me bring my x-axis down a little bit. And you may need to futz with things a little bit, move it around, make it make sense for what you're trying to do. Okay, so next up, label. For this class, for the most part, it'll always be X down here and Y up here, unless you're graphing a word problem, you're graphing something in particular that has names. In the next class, if you keep going to Algebra 3, we do all sorts of bonkers things. So don't assume it's always X and Y, but for now it will be. And let me plot some points. I'm going to do my scale will be 1, 1. So like this will be negative 1, negative 2, 1, 2, 1, 2, 3, 4, 5, 6, 7. You do not have to write in all the numbers. I'm doing this just because we've just started the graphing, and I'm thinking maybe some people might be a little bit rusty. So I'm writing in all the numbers. Now, some people ask, okay, how many numbers do we need to put on our graph? Well, math teachers are all sure, I am sure I've got the best way to do this. And the way I want to do it is you need at least one value on the x-axis and one value on the y. That's enough to extrapolate the rest of the scale. So you need at least one value. So 2 values altogether, 1 on the x, 1 on the y. If you want to fill in more, that's awesome. Some teachers may want to see more. They want you to demonstrate you really know what's going on. So just follow their lead. Every teacher's got a different idea about what's the most important thing. And all together, hopefully with all the different teachers, you end up learning all the important things, and then bam, you know everything and you're brilliant. Okay, 0, -2 is right there. 0, -2 is right there. 1, 1, 1, 1 is right there. 2, 4 is right there. 3, 7 is right here. Now I changed directions. I went to -1, -5 is right here. And then 1/3 -1 is not going to be easy to graph, but I'm going to guesstimate it. There's 1, right? So I go about 1/3 of the way over on the right and then down to 1. Now, if I have graphed this carefully enough, hopefully you see a pattern. Do you see that pattern? All these points lie on a line. And this is where the graphing becomes possible. Now, remember I said we have to graph an infinite number of problems in a finite amount of space, an infinite number of ordered pairs in a finite amount of space. This is how we're going to do it. If we get a sense of where the line is, all the points are going to lie on this line. And again, freakishly devoted to the arrows. So there's my line. I can make it look all pretty by writing its name, giving it a little name tag. Again, follow your instructor's leads. Different instructors think different things are tragically important. One thing I will point out, remember we saw that really interesting thing that when x went up by 1, as x goes up by 1, so you go 1 to the right, you go up 3, and there's your next point. Over to the right, 1, 1, 2, 3. 1, 1, 2, 3, 1, 1, 2, 3. That is a real pattern, and we're going to see that in the next section. That will be called the, do you know what it's called? Yes, it's called the slope. Woo! Okay, so here's the thing that I cannot prove to you, and you just have to take my word for. I'm going to wave my arms around and say magic. A linear equation in 2 variables is an equation with 2 variables, x and y, usually x and y, could be 2 others, which only appear to the first power. So we don't have x squared, no y squared, are not multiplied times each other, no x times y, and do not appear in the denominator of a fraction, no 1 over x or 1 over y, and also no x inside a square root. So no shenanigans, plain. An x, maybe times a number, a y, maybe times a number, or just by itself times 1. If we have that situation, then the graph of a linear equation in 2 variables is always a line. And why is it always a line? Well, look at the name. Linear comes from the word for line. So I just gave you this massive, amazing piece of information, and it's just for free because I can't prove it to you in this class. And all we could do is take a bunch of examples, and then you could believe me eventually. So this is something that gets developed later on, and I could prove it to you once you finish calculus. Come back and let's talk about it. But for right now, we just take it as a given. If you get a linear equation, which is what you're going to get in this chapter, chapter 2, then you know the graph will be a line. So you're going to need a ruler. But the good news is if you already know it's a line, I mean, I didn't need to use 6 points here. I really only needed 2 or 3. That would give me an idea of where the line is. So that's something else we're going to be using. We're going to say, heck, if we know this is a line, I'm just going to find a couple of points and bam, I got it. Okay, so that's it for part 1. In part 2, we're going to continue on, learn some other ways to graph lines. Woohoo! Yay! Okay, guys, math on, woohoo!